So, today we're going to be looking at predicate logic, specifically the syntax of predicate logic. Tomorrow at 2 p.m, Hux will be looking at the semantics, but we're going to be looking at specifically how to form predicate logic expressions and how we can evaluate them. So, propositional logic, it allows us to state facts, but two things it doesn't allow is we can't state properties of objects or properties of elements of the domain, and we also can't accurately represent relations between objects of the domain. So, what predicate logic does is it introduces this domain and we can reason about members of the domain. So for example, say our domain was natural numbers. We can bring in numbers like 0, 1, 2 and we can reason about them. So we can create these predicate functions and these will evaluate to something which we're going to take a look at in a second. But all this does is introduce a domain and a few extra symbols which we'll look at. Okay. Famous Socrates argument. All men are mortal, and Socrates is a man, therefore Socrates is mortal. So we can use predicate logic to represent this argument here. We can say P of X is... so we can say that this first line is the same as saying P of X implies Q of X. So can anyone tell me what P of X is representing here and what Q of X is representing here? What do these two predicates mean? Yeah, perfect. So P of X represents the property of, or I'll say X is a man. And then Q of X is saying X is mortal. So we can change the element of the domain that we're passing into these predicates to change what we're saying. So if this was Y, we'd be saying Y is mortal. So all we're doing here is saying P of X, if X is a man, then X is mortal. And what this part here says is, so this symbol here means for all. We call this a universal quantifier. And so for all X in the domain, in this case our domain would just be people. Let me write that actually. So our domain is just people. For all values of X in the domain, if X is a man, then X is mortal. So that's this line being represented here. And then we're saying P of S maps to Q of S. So P of S, we're saying S represents Socrates. This is a constant. So this is a specific element, a specific object in the domain. And we're saying this implies that they are mortal because we can gather this from this. Okay. So all a predicate is, as we looked at here, these two are predicates. So all a predicate is it's a symbolic function where we can represent a statement or assertion in relation to a specific object. I believe this is maps too. I mean, I would have opted to put this, but looking at some of the notes, they decided to use this. Yeah, so this sort of implies. Yeah. Okay, cool. So, yeah, let's move on. Okay. So predicates, symbolic functions, and all they do is they take some object or some variable from the domain and they return a truth value. So what are our two truth values? Yeah, let's just get this cleared up. I mean, I would say this makes more sense, but ABC. So A, B, C. D is the same as A and B. Oh, okay, that makes sense. Right, so I guess if you have multiple things, you can basically say all of the statements that precede it lead to this, not just the single statement that precedes it. I think that's what Hux is getting at. Because that would make sense to me, having... Yeah, okay. So yeah, implication just looks at the last thing that precedes it. But you mean, yeah, consequently, that's a good way of thinking about it, I guess. As a result of everything beforehand, that leads to this. Okay, cool. Okay, so what are our two truth values? Well, how could we logically write our two truth values? So we looked at attack, and we looked at this upside down. So these represent what? What do these two symbols represent? Yeah, perfect. So this is true, this is false. So all the predicate does is it takes some element of the domain and it converts it to true or false. Good job, Ali. Okay, so in Socrates' arguments, what would our predicates be? All they would be is these two things here. And these would return either true or false. So Px would return true if whatever x is a man, and Q of x would return true if whatever x is mortal. Cool, okay. So predicate logic introduces two things called quantifiers. And a quantifier creates a scope. So these are two quantifiers that we need to be aware of. So we have the universal quantifier. And all this means is for all elements of x in the domain, something is true. So whatever precedes this or whatever comes after this would be true. And then we have an existential quantifier. So this just means there exists some element x in the domain such that, and then whatever we put after that. So those are these two quantifiers. Are we good with that? If there's no questions, I'll assume we are. Perfect, okay. Okay, so in predicate logic, we also have variables. Variables are symbols we use to represent objects in the domain. And the reason we use variables and we don't use the actual object itself is because we don't know what that element it's representing is. It's an yet unknown object in the domain. So in this predicate logic statement, x and y are two examples of variables. These two would be predicates, which we've looked at previously, but all of these sort of yellow characters represent variables. Now, variables can either be free or bound in a predicate logic statement. So, could someone explain what free means and what bound means? What's the difference between those two? What makes a variable free and what makes it bound? Bound, yeah, perfect, good job. Okay, so yeah, bound is where it's in the scope of some quantifier. It's defined by this quantifier and we just use it in that scope. Whereas free, it's not defined by a quantifier, it's just a variable we can use globally. You can almost imagine it as if you have some Python code, for example, you have local variables in a function and then you might have some global variables. So free variables you can imagine as global, whereas bound, they're local to some scope. So in this statement here, I mean, it wouldn't actually apply to this statement here because the scope of this for all quantifier is this whole expression. So even though x is bound by this quantifier, in this whole expression, it's still in the scope. Whereas y is free because there's no quantifier. There's no, for example, there exists a y or for all y, which is spawning this y in, if that makes sense. And so, yeah, constants, as we went over, they're just specific objects in the domain. And variables represent unknown, as yet unknown objects in the domain. Does that all make sense? Okay. Cool. Let's move on. Right. Functions. So, functions build some element of the domain from an existing element of the domain. So, for example, let's say we had a function called add1, and all that does is it just returns 1 plus something. We can pass in something in here. Say we pass in 2, and that would return something like 3. So this is an example of a function. The reason it's a function and not a predicate is because we're not returning a truth value here. We're returning true or false. No, we're not returning true or false here. We're returning another element of the domain. For example, natural numbers in this case. And so it's a good thing to remember not to get functions confused with predicates. Now, f to the power of k, or you might see it written like this, just tells us that the function f has arity k. What is the arity of something? Could I get a quick definition of that in chat? What is an arity? What do I mean by that? Yeah, good. So number of arguments. So arguments are what we pass into something, and then parameters is what we sort of receive on the receiving end of the function. But yeah, so this is a number of arguments we pass in. So what would be the arity of this function here? 1. Good. We're just passing in one argument. So arity equals 1. Cool. Okay. And final side note on this. The pair of a collection of function symbols and a collection of predicate symbols, along with their arities, we call this a signature. I'm sure Herx will have a lot to say about that, but that's just something to keep in mind. We can represent an entire set of functions and predicate symbols with their arities in this huge thing called a signature. Yeah. Okay. So that's functions. So we looked at functions, predicates. We've looked at variables and constants, and we've seen that variables can either be free or they can be bound. Okay, let's move on. Okay, this is the syntax of predicate logic. Don't worry if this is a bit overwhelming, but all this is saying is in predicate logic we can have sort of two types of terms. We can have a single term, which is just one thing, or we can have a predicate. A predicate is made up of... Sorry, no. P represents a statement. So we can either have P... This lowercase p is a predicate. So let me just highlight that difference there. So this is a predicate, and this is a statement. So we can either have a predicate, which takes in some values and returns true or false. We can have the negation of something, which is true or false. P and P. So we know something... P here is true or false. P here is true or false. So the result of this will be true or false. P or P, again, this will be true or false. P implies P will be true or false. For all x, P. So these two are the new ones we're seeing in predicate that we didn't see in propositional. For all x, P. So this is just saying the predicate P is true for every possible value in the domain. And so this will also just return true or false. And then this is saying there exists something in the domain that makes this predicate P true. So again, that would be true or false. So this P will always result in something that's either true or false. Whereas T is saying, okay, X, so some element of the domain. So T is defined as some element of the domain or a function which takes in a bunch of terms. So is this going to be a truth value or a term? What do functions return? Yeah, good. So this will always return a term in the domain. This will always return a term in the domain. So this will always be some element in the domain. And so you can almost imagine this as the two sort of types that we have in predicate logic. We can either have a truth value, which is just a proposition or a statement, and then we can have a term, which is just some element of the domain. And so terms are just single terms or they're functions of existing terms, and propositions are just predicates or negations, ands, ors, implications, universal quantifier or existential quantifier. And so that's how we can make up larger predicate logic expressions. Okay, let's move on. Does this all make sense? Are there any questions about this? Anything anyone's unsure about? Good, good. Okay, let's move on. Right, so we call this the substitution operation. So what this says is we replace all of our free occurrences of x in some proposition P or some statement P with the term T. So if we had something like P is defined as, okay, let me think, f of x. Okay, so if we applied px, replacing x with t, all that would do is it would replace our occurrences of x. In this case, it's just this, all of our free occurrences. So this would become f of t, or g of y implies h of z. But one thing to remember is that's only talking about free occurrences. So if we had something like this, write this out. Okay, so let's say we had f of x and g of y implies that okay, so what would this look like if we applied the substitution operation to this? What would p replacing x with t be? I'll give you a moment to take a look over that, then I'll go through it. Only the first x is changed to a t. Yeah, good. So this is our free occurrence of x. Both of these two are bound by this universal quantifier, and so we don't change these because they stay bound in the result. The only thing we change is this free x, and we change that to a t. Yeah, good. Perfect. Okay. That will make sense. I hope so. Okay. So these quantifiers, they introduce a few new rules. So we have for all elimination, for all introduction, and then we have existential elimination and existential introduction. So you have an elimination rule for both of them, and we have an introduction rule for both of them. So you can get rid of it, and we can get it into our proof. So let's start with for all elimination. Can I zoom here? Perfect, I can. Okay. So for all elimination, if we know that for all values of x, the statement p is true, then we can gather that p is true for some other variable or some other term y. And so this is an example of for all elimination. If we know, for example, for all x, f of x, then we know, let's say let's say our domain's natural numbers. Can I make this pen a bit smaller? Okay. So yeah, let's say our domain's natural numbers. Then from this, we can gather that f of 2 is true. We can gather that f of 2 is true. We can gather that f of 3 is true, because we know that for all values of x in the natural numbers, this predicate f will always, this function f, sorry. No, this predicate f, because it returns a truth value, will always return this will always return true. And so that's for all elimination. Then we have for all introduction. So this is the opposite. And what this is telling us is, if we know p of x, y, so this is saying if we know some predicate's true for some general term y, then we can say that for all values of x, p is true, because we've proved it for some general term. Note that this can't be a t. This can't be a constant. This has to be a variable which isn't bounded by anything. This has to be a free variable. And so this is how we can introduce a for all into our proofs with for all introduction. Okay, and then we have, okay, we'll come back to this. Then we have existential introduction. So all this is as long as we have proved that for some term t, that a proposition p is true, then we can gather that there exists some value in the domain, because t is that some value. So there exists some value in the domain that makes p true. So this is how we can introduce an existential quantifier into our proofs. And finally, to get rid of the existential quantifier, that's this fun proof here. Okay, so if we assume that there exists some x in p, then we can gather this. So we can get an assumption saying, okay, so p is true for some term, let's say y. One thing to note, this is a term. This is not a variable, this is a term. And so if we know that given p is true for some term y, if we know that p is true for some term y, and from there we can gather q, then we can come to the conclusion that q is true. Because if we know there exists some x such that p, and p is true for some term y, then we can gather Q. One thing to remember though is you can't pick and choose this term. This has to be a new fresh term that we've not seen. One thing Hux has said is in the for all introduction, be careful with free variables. Yeah, so you want to make sure that we don't have free variables in for all introduction. Hux, are you talking about if we have? Oh, okay. Okay, so. And has no. So. Oh right, yeah. Okay, so you want to make sure that you're not using bound variables here, right? Is that what you're getting at? So y needs to be free, right? Y needs to be bound. Are we sure? Okay. I think I'll just leave it like that for now because I don't want to put anything that's not fully correct on there that I'm not fully sure of. But yeah, just something to keep in mind. Make sure that what you're doing, just make sure that it logically makes sense. That you're not saying that for all something is true by just being given a term. It has to be something solid. Yeah, that's not the best exhaustive explanation, but that's the 4 rules it sort of introduces. So I wanted to have a go at a few predicate logic proofs because these proofs are quite fun. But before I do that, is there any of these slides or anything we've covered that anyone's unsure about? I'll just scroll through the slides. Let's see the examples. Okay, let's free unbound variables, functions, make a value in the domain, not a true or false value. Syntax of predicate logic, substitution operation, and the rules. Okay, let's have a go at a few proofs then. Okay, this is the first one. So, for all x, there exists some value of y such that p of x implies q of x. And this whole thing implies not q of x implies not p of x. Okay, so how do we start by proving this? Where do we start? Implication introduction. Okay, good. So make that bigger now. Okay. Not q of x implies not p of x. And this would give us an assumption. This would give us that first whole bracket as an assumption. So now we know for all x, there exists a y such that p of x implies q of x. Okay. What do we want to do next? Good. Another implo intro. Oh, I didn't label that actually. Okay, so we do another implication introduction and we get not q of x as another assumption. Okay, what do you want to do next? So if we look at it, what we're trying to prove is the contrapositive. Negation introduction. Okay, so 3, negation introduction, good. And that gives us what assumption? That we can now work with. P of x, good. Okay, so now we've got P of x to work with. What can we do with that? So we know we need to reach false here. How can we get false? P of x. Yeah, so we're going to have a contradiction. We're going to have q of x and not q of x. And this rule would be negation elimination. This rule would be this. Can you use rules like DNE and LEM? You often, I don't think we'd have to use LEM or DNA. But I believe predicate logic sort of also breaks down into classical and constructive. Most of the predicate logic that we've been doing is just constructive predicate logic. So if the question says use classical rules, yeah, as Ash said, then I don't see an issue with using it, but I'd just try and stick to constructive with predicate. Okay, so yeah, we have this contradiction here, and how can we gather this contradiction? How can we, so we can get not q of x from our 2 assumption. How can we get q of x? Okay, good. So we can say p of x, and p of x implies q of x, and this would be implication elimination. Okay, p of x we can get from 3. That's simple. What about this? How can we get this? Existential elimination. Okay. So let's say there exists a y such that p of x implies q of x. And this would be our existential elimination. Okay, how can we get this now? From for all elimination. Good. So for all elimination. And then we can bring up that fat assumption 1. So for all y, for all x, there exists a y such that p of x implies q of x. This exists a y is actually redundant in this entire proof. It's just there. So we close that with 1, and there we have it. We have our proof. So we've proved that this implies this. What have I done wrong? Let me know if I have got something wrong. Existential. Oh, yeah, you're right. This isn't existential elimination. Don't know what I did. Okay, let's go back a few steps. Okay. Yeah, you're right, Ash. My bad. Okay, existential elimination. We can't just get rid of the sign, unfortunately. Okay, existential elimination will give us another assumption. It will give us assumption 4. What would our assumption be for 4? P of x implies q of x. Yeah, good. We'd replace all of the bound occurrences of y with some new term, but because y isn't used in this whole thing, we just don't need to replace anything. Okay, and so we can put that here, because this is what we want to get to this conclusion. This is our q in that rule, so we can just close that with a 4. We don't actually have to do anything else there. Does that make sense? That part. Okay, cool. And then, as you said here, what we'd do here is we'd say, okay, for all x, I think as Victor said, for all elimination, p of x implies q of x. If we know it's true for all values of x, we know it's true just in general. So we can say this is our for all elimination, and that would be our complete proof. So we've proved that this whole chunk here implies this here, and this is like the contrapositive, but in good. So what we did here was just replacing x with x. Cool. Okay. If we just trace through that, so we've done that, we did an implication elimination, another implication elimination, and then we did a negation introduction. So we wanted to get false. We did that by getting the contradiction of q of x and not q of x. Because q is a predicate, it returns true or false. Then there'd be a contradiction if one is true and one is false. So that gets us to false. We can easily close the q of x with our assumption 2. And on the left hand side, to get that q of x, we use our p of x, and we show that 3 and 1, our 3 and 1 assumptions have a contradiction. And so we did that with an existential elimination to get p of x implies q of x. And we could close that with the assumption we just got, assumption 4. And then that existential, we just get from a for all elimination, mapping x to x. So we did our substitution operation here. Cool. Does that make sense? Are there any questions about any of the steps here, if anyone's unsure about anything? Perfect. I think I've got one more on here. This one's slightly longer, but let's have a go at this one together. I'll give you a few. Actually, I'll give you a few minutes to maybe have a go yourselves, or if anyone wants to come on stage and talk me through it, we can also do that. If anyone wants to come up, just raise your hand. If not, just send me what the first step you want to do is. Yeah, Hux, that'd be great. Let me invite you up.
What's up, gang? Cool.
This is recording your voice. Okay, cool. What do you want to do first?
The first thing we're going to do is we're going to take those first two parts of the if statement and make them our assumptions. So by applying implication introduction twice.
Good, okay.
Assumption number one then is for all x, if p of x, then q of x. Perfect. Assumption number two is for all y, if q of y, then r of y. And we are trying to prove that if there exists z such that p of z, then there exists w such that r of w. Cool.
Okay.
We're going to do a third implication introduction.
Okay.
And have assumption number three be exists z such that p of z. And a general rule of thumb is if you assume it exists, you then do an existential elimination immediately after. So we're going to eliminate that assumption 3. So then you'd have exists z, p of z, with a line of 3 on top of it. And then on the right side, you'd have exists w such that r of w.
Okay.
And so assumption number 4 would be, let's go p of c. I don't know.
Let's use j.
Okay, p of j.
Okay, cool.
Cool. So we have p of j, and we're trying to get to there exists w such that r of w. We can use for all elimination to get p of j, if p of j, then q of j from assumption number 1.
Yeah, okay. So we can say, so we can get q of j, and then what do we need to do with q of j?
Well, then you pass that into if q of j, then r of j, which we get from for all elimination on assumption number 2.
Yeah, good. So
an accidental introduction.
Perfect.
To get exists w such that r of w.
Cool. Okay, so we have our existential introduction here, and then we have q of j implies r of j, which we get from
No, that was y.
Y. Perfect.
And then also requires a q of j to eliminate that if. And we get that q of j from an implication elimination from assumption number 1.
Perfect. Okay, this is a bit messy, but I hope that makes sense to everyone. Thank you, Hux. Appreciate that.
No worries.
Cool. Okay, are there any questions about what I've done here? Anything anyone's unsure about? I'd be happy to just clear things up. So we know that we can get p of j is true. From there, we can say, okay, p of j implies q of j, and then we can say q of j implies r of j, and so there exists some term where r is true, this term j that we made. Don't forget to close. Ooh, you're right. Yeah, this needs to be closed with 1. Good job, Victor. This is kind of proof that is transitive. Yeah, so we're saying p of j implies q of j, and q of j implies r of j. So we're saying kind of we want to prove this implies this. I guess, yeah, I see what you mean. Cool. If there's no questions, that is the end of the slides. Oh, did I? No, you should have said Ash. I like the feedback. Okay, this should be closed with assumption 1. Cool. Okay. Awesome. I like being told I'm wrong, exactly. Okay. If there's any questions, anything anyone's unsure about, let me know. Also, just let me know in general. I'd be happy to sort of help out with that. But if not, that's the end of the session. This will be uploaded to YouTube. Be sure to come to the predicate logic semantics tomorrow. I'm sure that will also be great. But yeah, thanks for coming, guys.